Now we would actually define permutation branching program. So this is one way of defining. We will give another way of defining a permutation branching program in terms of instruction, and then we will see why they are equivalent. That is quite easy to see. So formally, so a program P is a set of instructions of the form I, G, H where I is a number between 1 and n, and G and H are permutations of well, so we only need it for 5, but it can be for anything. So let us say we define this only for with 5. So a permutation branching program over S5. Okay, so for the rest of this lecture we will fix the width to be 5, because as I said 5 is good enough for us, but this can actually be defined for any constant over here. Instead of 5 I can have any w. So if G and H belongs to S5, so there are two permutations in S5 such that and the instruction outputs G if xi is 1 and it outputs H if xi is 0. Okay. So an instruction is said to output the first permutation if the bit xi is 1, and it is said to output the second permutation if that bit is 0. Now what is a program? So a program is a set of instructions. So it is not just a set. So again set is not the correct word here. I should write it is a sequence of instruction, because the order actually matters. Okay. So now the length of the program is the number of instructions, and the output of P is the product of the output of all the instructions in the sequence. So this is why the order is important, because I just compute. So what do I mean by output of all the instructions? So for each instruction I know what it outputs to, either 0 either G or H. So for the first instruction, let us say it outputs to some K1, the second instruction outputs some K2, then K3. So the output of P will be product of K1 up to K whatever is the length. Okay, if L is the length, then it is L. So now how is a language accepted, or how is any input accepted? So, for an input to be accepted or rejected, I have to define the notion of acceptance and rejection. So, P okay, P 5 cycle recognizes L on inputs of length n if there is a permutation sigma not equal to identity in S5 such that okay, for x belonging to L, P outputs sigma, and for x not in L, P outputs the identity. So, E is the identity permutation. Okay. So, again there is nothing special about E or sigma over here, it is just choosing two different permutations. Okay. So, if x is not in L, we choose the identity permutation, and for x in L, we choose some permutation different from the identity permutation. Okay. Now, yes, as I said that the product again would represent some permutation, and if that represents sigma or E, then this is what we do. Now, we also call this as, also referred as P sigma recognizes L. Okay. So, if such a thing happen, we say that P, the program P sigma recognizes L. Now, the question is, so I have
sigma is a factor or something like that. 5 cycles, that's why it's called a 5 cycle permutation.
yeah, right. So, sigma is not just any permutation, it is a 5 cycle, yeah. So, sigma,
then there was a proof like any 5 cycle is,
yes,
we can convert it to some other.
it's a conjugate. So, any two 5 cycles are basically conjugates, yeah, correct. So, if sigma not in E is a 5 cycle in S5, correct. Is a 5 cycle. So, it is not just any permutation. So, this is a good point, it is a 5 cycle. Okay. So, now how is this, yeah, I mean how is this notion equivalent to this notion? How can I go from here to here? So, suppose if I have a program P which recognizes a language, how do I get a bounded with or a with 5 branching program that recognizes that same language?
Basically gives the edges going from there, right? So like G gives the one edges and H gives.
Exactly. So, to see that this can be represented in the earlier form, we note the following. So, first of all, each instruction will correspond to a layer. Okay. So, for example, if I have my first layer, that would correspond, so the first instruction would correspond to the first layer. So, this is my, let us say, layer 1. Whatever variable is there in the first instruction, I will have that same xi over here, and then whatever is the instruction, whatever is the permutation g, that would correspond to all the outgoing edges that are marked by 1. Okay. So, all the outgoing edges that are marked by 1. So, this is my g over here, and I can use a different color. All the edges that are maybe, actually this is very similar, by 0, suppose. No. So, this would correspond to the permutation H. Now, what about the start and the accept node? How do I define the start node and the accept node here? So, for the start node, what we would do is, so we know that sigma is not identity, okay, which means that so since sigma is not identity, there exists some I such that sigma I is not equal to I. So, for the start node, we choose set S to be equal to ith node in layer 1, and label the node sigma I in last layer as 1 and all other nodes in last layer as 0. Okay. So, now it is easy to see that, well, if there is a, if let us say x is accepted, which means that the product of these permutations would correspond to sigma, which means that well, if the product of the permutations correspond to sigma, then the entire thing basically is represented by sigma, which means that there is a path from I to sigma I in this program. On the other hand, if the product, if x is not in L, then the product would correspond to identity permutation, and we know that sigma I is not equal to I, which means that it goes to some node that is labeled 0. Okay. So, this basically it's not an equivalence as such, but at least it is showing that any program in this form can be converted to a program in this permutation branching program. Okay. The other direction actually can be worked out, but we do not need it for this proof. We only need this one direction, because if we show that any, so now what we will show is that any language that is accepted by NC1, for any language accepted by NC1 circuit, there is a program of this form that accepts that language, and by this thing there is a permutation branching program, which is anyway a branching program. Okay. So, to establish the theorem, we will prove two lemmas first, and these two lemmas are essentially just simple group theoretic ideas. Anything else? Okay. So, there exist two 5 cycles G and H such that G H G inverse H inverse is also a 5 cycle. Okay. So, two permutations that are 5 cycles exist. So, this is also in group theory, this is also called the commutator of these two elements. This is also a 5 cycle. So, the proof is nothing but just constructing two 5 cycles. So, the first 5 cycle would be, let us say, let G be the 5 cycle 1, 2, 3, 4, 5, and H be the 5 cycle 1, 3, 5, 4, 2. Now, we correspondingly have G inverse and H inverse. So, then G inverse is just, so this notation means that if you are not familiar, it just means that 1 goes to 2. In this permutation G, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. Here 1 to 3, 3 to 5, 5 to 4, 4 to 2, and 2 to 1. So, what is the inverse of G? So, 5 will go to 4, 4 goes to 3, 3 to 2, 2 to 1, and similarly H inverse would be 2, 4, 5, 3, and 1. And now we can check what G, H, G inverse and H inverse is, and this turns out to be, I mean, you can calculate it, it is just 1, 3, 2, 5, 4. Okay. We can maybe just check one of the input. So, let us say if I check for 3, so in G 3 goes to 4, here 4 goes to 2, then in G inverse 2 goes to 1, and here 1 goes to 2. So, here you can check that 3 is going to 2, and the rest can be checked similarly. Okay. So, this is just observation. Now, the why, now the question is why this? Why are we looking at 5 cycles, and why do we need this? Okay. So, this intuition I will just come to, I mean I will just come to this point in a while. Okay. Why suddenly we have these magic 2 permutation, and what is the utility, what is the application of this? The next one is another very standard result in group theory. Yeah, so as I said, this again actually follows from a very standard result in group theory. So, let sigma and tau be 2 5 cycle. So, if P sigma recognizes L, then there exists a program P prime of same length such that P prime tau recognizes the same language L. Essentially what we are saying is that, well, I can change this permutation without any blow up in the program size. So, if I have any language that is accepted by some 5 cycle sigma, I can actually go to another program of the same length for any other 5 cycle. So, this gives me the flexibility, and this just follows from a simple observation that, well, for 2 5 cycles sigma and tau, okay, there exists a permutation, need not be a 5 cycle, permutation phi in S5 such that tau is equal to phi sigma phi inverse. Okay. So, this term is called the conjugate of sigma. So, it says that any 5 cycle is basically a conjugate of another 5 cycle, that is all. And this, as I said, is a very standard result, it can easily be checked. Now, how do we get P prime from P? Very simple. So, suppose P was of the following form. Okay. So, suppose P was consisting of the instruction M1, M2 up to some ML, okay, where Mi had the instruction, let us say, I think so, it is some Ji, Gi, Hi. Okay. So, on this, on the bit, so Mi has the index Ji, and if Ji is 1, then it goes to the permutation Gi, if Gi is 0, it goes to the permutation Hi. Okay. Now, we define Mi prime to be Ji phi sigma phi inverse, not sigma, phi Gi phi inverse and phi Hi phi inverse, then P prime, which would be M1 prime up to ML prime, tau recognizes the language L, because very simple. So, if I look at the product of all these permutations, okay, so all these phi inverse and phi of 2 adjacent permutations will cancel off. Finally, what I would be remaining with phi product of all these GIs and HIs, whatever they are, phi inverse. Now, the product of all these GI and H, we know that it is, for us it is sigma if x is accepted, and it is identity if x is not accepted, and that is exactly equal to tau. Okay. So, very simple. Again, this is a very standard graph theoretic application of group theoretic application of this result. So, now we come to the main proof of Barrington, and that is also actually quite simple given these observations. So, proof of theorem 1. So, let C be a NC1 circuit consisting of AND and NOT gates only. So, using De Morgan's I can remove all OR gates, and it is an NC1. So, all these gates have we can assume they have fan in 2. Yeah, so without loss of generality we can assume this. So, now what we do is that we prove we show let C be a NC1 circuit of depth D, consisting of AND and OR gate. So, we show by induction on D that there exists a program accepting the language of C of size at most 4 to the power D. Okay. So, we will prove this statement by induction on D. Okay. So, the induction is where we will use this. So, let us see how the induction goes. So, for D equal to 0. So, D equal to 0 means that I do not have any gates. So, either my nodes are a variable or a constant. Okay. So, if I mean the circuit is either it has variables or constant. So, if C is some variable xi, then add the instruction I sigma E if C is the constant 1, then add 1 sigma sigma if C is the constant 0, okay. So, you can easy to see that, well, if C is just a variable xi, then if xi is 0, this instruction would output E. If xi is 1, the instruction would output sigma. If C is 1, then in either case it outputs sigma for any variable 1. So, 1 is just some candidate variable, does not matter, otherwise it is outputting E. So, in this case we can see that there is one instruction if D is equal to 0. So, it is bounded by 4 to the power 0, which is 1. Okay. Now, assume for D or assuming for D it is true, we prove for D plus 1. So, we assume there is a program of size at most 4 to the power D for a circuit of depth D. Now, if C is a circuit of depth D plus 1, how does C look like? Okay. So, for D plus 1, so there are two forms. So, C can be either of the form, the top gate can either be a NOT gate or it can be an AND gate. So, suppose the top gate is a NOT gate. So, C is something of the form NOT of C prime. So, we know that there exists P of size at most four to the power D that, let us say, sigma inverse recognizes L of C prime. C prime is a circuit of depth D. So, we know that there is some program. So, actually, even if I say that okay, there is a program which sigma recognizes L of C prime, by applying lemma 3, we get another permutation that would recognize it for some other 5 cycles. Sigma prime is just another 5 cycle. So, we can actually take this to be anything that we want. Now, how do I get a program for C now? What will it be? So, construct or just to make keep consistency between the notations, let me write this as P prime. There exists P prime of size at most 4 to the power D that recognizes L C prime. So, now we construct P by doing what? By So,
sigma in both ways.
Yeah, so basically I will add one more instruction. Okay. So, by adding the instruction 1 sigma sigma to the end of P prime. So, as you said, apply sigma in both cases. So, to the after P prime I add one more instruction 1 sigma sigma. So, now if P prime was outputting sigma, this would output E. Okay. That is, if P prime was accepting an input, then P would reject it, and if P prime was outputting E, that is, it was rejecting, this would output sigma. Right. So, if accept becomes reject and reject becomes accept, and what is the size? So, the size increases by just 1. So, it is anyway bounded by 4 to the power D plus 1. Okay. So, this is the easy part. Now comes the difficult part, that is and that is where we need this commutator idea. So, suppose C is of the form C1 and C2. So, by induction we have P1 of size 4 to the power D that G recognizes L of C1 and P2 of size at most 4 to the power D that H recognizes L of C2. Okay. Again, they can be recognized by with respect to any permutation. We applied lemma 3 and we can get it with respect to this G and H. So, note that G and H are the fixed permutation that we defined in lemma 2 earlier. Okay. So, G and H is this very special 2-5 cycles. Now, we apply once again we apply lemma 3 and we get that P1 prime of size at most 4 to the power d, that G inverse recognizes L of C1 and P2 prime that H inverse recognizes L of C2. Again I apply the lemma 3 and I get it for G inverse H inverse. Now what we claim is the following. I should have kept, okay, does not matter. Then P, which is equal to P1, P2, P1 prime, P2 prime. What was that permutation called? 1, 3, 2, 5, 4. 1, 3, 2, 5, 4 recognizes L of C. Okay. How is that? So, this is just by looking at the truth table to see this note. So, we have C of or okay, we have C1 on X, C2 on X, P1, P2, P1 prime, P2 prime and P. So, C1 and C2 on X can have any of the following outputs. It can be 0, 0, 0, 1, 1, 0 and 1, 1. These are the 4 outputs for C1 and C2. Now, P1 and P2 are or P1 and P1 prime are programs for C1. Okay. So, for 0 P1 would be E, P1 prime is also E, and for 1 this is P1 is G and P1 bar is G inverse, right. Similarly, P2 is E and E over here, it will be H, H inverse, E, E, here also H, H inverse. Now, how do we define P? So, P is just the product of these permutation. So, product of E's is E, product of E, H inverse is again E, G inverse, E inverse is again E, and G inverse, H inverse is my special permutation 1, 3, 2, 5, 4, and this is exactly what AND is supposed to do. So, this completes the proof. Okay. So, now coming back to the point that why did we choose these permutations as my G and H. Okay. So, as it turns out that if you actually go below 5, okay, if you go to 4 cycles, you cannot state this. Okay. So, there is no there is no 2 5 cycles or 2 4 cycles such that their commutator is also a 4 cycle. So, the minimum number that you have to come to get this property is 5, and actually these are just 2 candidates. There are actually other 5 cycles also for this is 2, you can choose any one, but this is just a candidate. So, that is the thing why we need to come to 5 at least, and for 5 it is actually sufficient for us. Okay. So, the rest is quite obvious. Okay. So, yeah, so as it turns out, actually the proof is quite simple. The proof does not have much, and it is very easy. The intuition is also very clear over here. But as I said at the beginning, that this was something that was not believed to be true prior to Barrington's work, and this is something that was a very big result at that point in time. Okay. Okay, so that is all for today. So thank you.